Hi everyone, in this application example we are asked to extract the problem table, the streams of this process from this process flowsheet and analyze it using a minimum approach of 10 Celsius. Data extraction is fairly simple, fairly straight, except for the hidden heat exchange in the recycle mixing. We have a first hot stream from 300 to 240, exchanging 405 kilowatts. This is a second hot stream. This is a little bit more tricky, from 260 to 250. This passes through for 220, but this is cool and then heated. And this is not probably the right solution. This is how this is working now, but probably you can do better. The real needs of this stream is going from 260 to 250, exchanging 540 minus 405 kilowatts. This give us 260 to 250, exchanging minus 135 kilowatts. The third hot stream is the condenser from 180 to 180, a flat one, exchanging 240 kilowatts. You can see it in the problem table. And then for the cold streams, we have the reboiler, a flat stream at 260, exchanging 300 kilowatts, and the outlet of the reactor, 180 to 200, exchanging 540 kilowatts. You can see those two here in the problem table. The last evident cold stream is the entrance of the reactor being heated from 140 to 250 with 2800 kilowatts. Remember that we cannot extend this stream across the reactor because the outlet is probably other thing, other material, different composition stream. And then there are the mixing streams. One, the hot one from 250, and an unknown temperature fresh feed that mix and go to 140 Celsius. The current solution for this stream is to mix it directly. It is cooling the hot and heating the cold to arrive to the 140 final temperature. But probably this is not the best, or it cannot be the best. Perhaps it's possible to use this heat from cooling the hot stream, or this heat from heating the cold stream away in a better way. And to analyze it, we have to include both streams, the cold and the hot one in the mixing, and try to calculate the minimum heating and cooling with and without those streams. As we don't know the entrance temperature of the fresh, we must make some heat balance. We can have the thermal inertia, the MCP of the hot stream. Well, this is an approximation, but we have the cooling and the heating in more or less the same range of temperature that gonna suffer in the mixing. That in both cases is 13.5 kilowatts per Celsius. And we have also the MCP of the mixture, because we have a change in temperature from 140 to 250, 2080 kilowatts, and these allow us to calculate the MCP. As an approximation, we can suppose that the MCP of the hot plus the MCP of the cold gonna make the MCP of the mixture. This is not considering mixing effects, but we have no better. Then, as a raw calculation, we can calculate the MCP of the entrance, and as we know the final temperature 140, then we are able to extract the initial temperature of the fresh feed. This is T2 and results 15.8 Celsius. This is a raw approximation. If you know the process in detail, you can simulate it or ask for the data. As for the current consumption, we have as heating 2800 in the preheater to the reactor and 300 in the reboiler. This made for 3100 kilowatts. And for the cooling, we have just the condenser that is 240 kilowatts. Now we have the complete problem table with the mixing streams, the hot and the cold mixing streams. Then we can apply the problem table algorithm and build the grand composite curve. You see 2860 at minimum heating and nothing, zero, at minimum cooling. This is a threshold problem, needing just heating, no cooling. This is using in excess of 240 kilowatts, that is a 7.7% excess in heating, and the whole 240 kilowatts of cooling, that is 100% excess. And we can make the same calculation of the problem table algorithm without the mixing streams. That give us the same minimum heating and minimum cooling, and of course the same excess. What means that? That we cannot make better use than mixing the hot and the cold mixing streams, and it's better to leave them as is, because mixing is simple, doesn't require equipment, and the efficiency of the heat exchanger is complete. And this is our analysis. This is all.